Boas tardes, noites a todos. É un placer ter hoxe con nós. It's a pleasure to have you here. Rakbat-Bi Abdyssagin. It's okay. Ele é un músico privilexiado. Naceu en 1999, ten 26 anos, e xa neste curto espacio de tempo, falaba antes con el, 4 doutorados en música, en diferentes temas, en diferentes universidades. Foi profesor e investigador visitante en Oxford, Cambridge, compuxo máis de 150 pezas, incluindo 4 óperas. Podría continuar moitísimo. O seu currículum é impresionante xa con tan curta idade. Contábame, falando con Fernando tamén, que, ele está aquí con nós desde onte. Onte non falaba español, hoxe xa sí. Today you already speak some Spanish, pretty good Spanish. En definitiva, é un auténtico privilexio telo hoxe aquí. Estará mañán tamén con nós, dando un concerto de piano neste mesmo lugar, con ese piano, e hoxe vai nos falar do seu libro Quantum Mechanics and Avant-Garde Music, que publicou o ano pasado, e, sin máis, espero que disfrutes da charla. Thank you very much for being here with us today.
Sí, muchas gracias por esta introducción. Estoy muy feliz de estar aquí y muchas gracias a CESGA y Centro Galego de Arte Contemporánea por haberme invitado con la visita científica a Santiago de Compostela. Esto es mi segunda vez en España y la primera vez en Galicia. La primera vez en España fue 10 años antes en Alicante, cuando tuve 16 años con conciertos con orquesta sinfónica. Y hoy voy a hacer la presentación con el tema mecánica cuántica y música vanguardia. Y ahora, por hablar sobre ciencia, prefiero cambiar a inglés. So, the topic of today's presentation is quantum mechanics and avant-garde music, Shadows of the Void, which is also the title of my eponymous book, which was published last year by Springer Nature and is available for purchase in bookstores. And in general, if we speak about music and science have very deep history of interrelations. The great physicist, one of the creators of the standard model of particle physics, Nobel Prize winner Steven Weinberg, even wrote that music might have been one of the first subjects which were studied mathematically. And it is believed that, as mathematician Ian Stewart wrote, the discovery that consonant intervals, octave, fifths, and fourths can be expressed as relations of natural numbers, 2 to 1, 3 to 2, and 4 to 3. This discovery led Pythagoreans to think that the entire world can be described mathematically. So for a very long time, music theory has been part of mathematics, and even in medieval universities, you had first trivium, logic, grammar, and rhetoric, and after that, there was a quadrivium, which were 4 mathematical subjects: astronomy, arithmetic, geometry, and music. And later, René Descartes, Marin Mersenne, Leibniz, Euler, all these great mathematicians, they made contributions to music theory. For example, Leonhard Euler's dissertation for habilitation was called Dissertatio Physica de Tono, which means dissertation on the physics of sound. Later, Euler created Tonnet's theory of interrelations of harmonies and tonal systems. And binary logarithms, which were formulated by Euler, they were first introduced in music as a way of subdividing octaves, and after that, Euler introduced them in mathematics. And later, in the 20th century, there are many creators like Yanis Xenakis, researchers and composers such as Milton Babbitt, Alan Ford, David Lewin, Gorina Mazzola, Dmitry Timochko, Eduardo Miranda, Carmina Cella, who all work in the direction of computational and mathematical music theory. But today's presentation will be different. Obviously, the first point of connection between physics and music is that the main elements of music are sound and silence. And to propagate, sound needs space and time. Space and time are described physically, and sound is a physical phenomenon, elastic waves. In quantized way, if quantized, they are phonons. But it is impossible to draw an equal sign between physics and music. But certain metaphorical and figurative correlations can be found. So today's presentation will not be about acoustics or mathematical structures in music, but rather it will be about chronological correlations with evolution of physics and the way of how different composers were implementing their understanding of quantum phenomena, such as Heisenberg's uncertainty principle, Pauli exclusion principle, superposition, and quantum entanglement, how this phenomenon of quantum mechanics were used to create music composition. So essentially about how composers interpreted quantum phenomena and used their understanding of them to create compositions and which were reflected on the deepest level of musical composition. Well, this book was reviewed in several outlets by some distinguished scholars, and one of the reviews which I liked the most starts with the phrase that if there was ever a book title that had the powers to elicit both fascination and dread in the minds of its potential readers, then it would surely be Quantum Mechanics and Avant-Garde Music. Coming to one of the main aspects of correlation, as we know, the main characteristic of natural sciences is that every theory and hypothesis has to be tested experimentally. Richard Feynman wrote that test by experiment is the defining feature of natural sciences. And this is one of the reasons why natural sciences in their methodology is very different from philosophy of ancient Greeks. If we speak about the creation of and invention of modern scientific method, we should mention the great Galileo Galilei. It is very well known that Galileo Galilei was one of the first to say that Earth rotates around the sun, and he had problems with Vatican. He was put in prison for that. But that's only one point of view. As physicist David Deutsch wrote in one of his books, there is one much more profound reason why Vatican was troubled with Galileo. It was not only that Galileo said that Earth rotates around the sun. Much more important was that Galileo was one of those who discovered and invented the scientific method. Galileo showed that to understand the world, it may not be really necessary to read Bible or books by Aristotle and other greats. To understand the world, you can make science. You can construct hypotheses and test them experimentally. Thus, Galileo showed an alternative way of learning about reality, about the world. And that was something much, much more dangerous to Vatican than simply saying that the Earth rotates around the sun. And later, thanks to Isaac Newton, his Principia Mathematica, that essentially laid the foundations of all the modern sciences as we know it. And in music, music also has its own experiment, which is a performance. To become music, a score has to be performed. We all know that a map is not the territory itself. It's only a description of the territory. In a similar manner, a score, la partitura, no es la música. The score is not yet the music itself. A score is only a description of the music. And only when a score gets performed, it becomes music. Another fundamental aspect of music is that music exists in time. Unlike visual arts, architecture, painting, which do not have an intrinsic element of time or performative time, you can, for example, look at paintings of Francisco Goya or Salvador Dali for 1 hour, for 10 days, for 10 seconds. It may change your perception, but this time is not dictated by the essence of a painting. There is no intrinsic time in the painting itself. But unlike visual arts, music always exists in time. There is no music without time. That was, for example, one of the points which were elucidated by spectral composer Tristan Murail, that music is an architecture evolving in time. So time is one of the foundational elements of music. And time is obviously a physical property. And currently the most successful theory of space-time is Einstein's general relativity. Many people ask, what was before the Big Bang? Or what was before the time was born at Big Bang? So according to Einstein's theory of relativity, general relativity, as it was said by Heisenberg, Feynman, Hawking, and other scientists, according to general relativity, Big Bang was a point when space and time were born. And space and time, they exist only together. And now, before, after, past, present, future are the instances which exist in time. There are no these instances without time. Thus, we cannot ask what was before the Big Bang or what was before time, because before there was no before, since there was no the time itself. And even the word was is not applicable to something that was before the Big Bang. And so even in music, every composer creates music in time. And there can be intrinsic developments of this music in time, so that certain elements evolve and develop within the structure of this piece of music as part of dramaturgy and form. But for a composer, he may perceive the entire piece of music as a single whole. So time is another fundamental aspect of music. An interesting thing is that, so this center is called Galician Center for Contemporary Art. What I do is called contemporary music or avant-garde music. Some people call it modern music. But there is a big question in terminology. The great physicist Gerhard de Hooft, in one of his books, wrote that the words such as modern or postmodern music, these terms might be not really correct, because music is always contemporary to its own time. So in future, the time may come when what we now call modern music or contemporary music will no longer be modern or contemporary music. And so Te Hooft made comparison with the term atom. Atom comes from the ancient Greek, which means undividable. But it is quite a misnomer, because we know that the elements, the particles which we now call atoms, are very well dividable. They consist of electrons and hadrons, and hadrons themselves are mesons or baryons, and baryons consist of 3 quarks, and mesons consist of quark and antiquark. So, according to the name atom, it might have been more, let's say, it should have been more correct to call not the atom, but elementary particles as we know them today, like leptons, phonons, quarks, as atoms. So this is another example of some things to which we accustom as a tradition, but are wrongly named. So even if we recognize that in the entire history, all the music was contemporary to its own time, we still call the music which was born at the beginning of the 20th century as contemporary music. Another important aspect of today's presentation is the idea of the void. So the book is called Shadows of the Void. There are many phenomena which are beyond our perception, which are very well beyond our perception, and which we tend to call the void. For example, human perception is fundamentally limited. We perceive the sounds only in the range from 16 to 20,000 hertz, and also we perceive only limited range of waves and what we see, and everything which goes beyond our perception we tend to call the void. But the big question is it really the void? Because what we call the void may affect our reality in no less profound way as everything material does. For example, we still do not know what exactly are the dark matter and dark energy, but together they constitute 95% of the current observable universe, according to the most updated cosmological data. So, according to this, we come to some philosophical ideas. One of them is that the void is not nothing. It is less than nothing, but more than everything. Second is that the void, or what does not exist, is more important than what exists, because what does not exist allows the existence of what exists. And the third point would be that mathematics is the language in which all sciences speak. So mathematics is the first and to date the most perfect virtual reality which has been created by humanity in order to describe the objective reality. And in music, silence plays one of the most profound roles. And for me, as I wrote some years ago, silence in music is an analog of zero in mathematics and the void in physical space. What we know as classical music was born after the emergence of classical mechanics of Isaac Newton and Newtonian theory of gravity. In music, it was reflected in a way that, for example, as Paul Hindemith wrote that, tonality in music became an analog of gravity in physical space. And also the sonata form, or even the sonata principle in music, can be seen as a reflection of philosophical dialectics. In this slide, we see three the most influential creators of that time. So Isaac Newton was the first, let's say, the first scientist in a modern way to say, who laid the foundations of all the modern science. Johann Sebastian Bach was probably the most influential composer Robert Schumann wrote that music owes to Bach as much as religion owes to its founder. And Immanuel Kant, with his critique of pure reason, was the most influential figure in philosophy of that time. And actually, Immanuel Kant was, by his training, first a physicist and a mathematician. And Kantian philosophy, critique of pure reason, is essentially philosophical metaphysics of Newtonian mechanics. So Kant's ideas about absolute space and time, they derive directly from Newton. And speaking again about Bach, a physicist, Frank Wilczek, winner of the Nobel Prize, once wrote that Bach was a great manipulator of patterns. And the great physicist, one of the founders of quantum mechanics, Werner Heisenberg, in his book Ordnung der Wirklichkeit, even made some correlations between mathematical group theory and the counterpoint and polyphony in fugues of Bach. But what we now call contemporary music was born at the end of the 19th and the beginning of the 20th centuries, exactly when the great discoveries were made in the world of science, which changed our perception of the structure of the universe, splitting the atom by Thomson and Rutherford, Einstein's theory of relativity and theory of gravity, and of course, quantum mechanics. And again, to repeat, no equal sign can be drawn between physics and music, but what we can find are metaphorical correlations. Here I show some correlations in timeline. I am not implying any direct connection between these events, but it is a sign that it was a time when every aspect of human endeavor, every field of intellectual activity was revolutionized. And it was impossible for contemporary music not to be born when every aspect of human intellectual activities were undergoing through a breakthrough. In 1897, Joseph John Thomson discovered electron, which was the first subatomic particle that was discovered. It is interesting to note that Joseph John Thomson got a Nobel Prize for discovering that electron is a particle, while his son, George Paget Thomson, later got a Nobel Prize for the discovery that electron is a wave. And this beautifully shows wave-particle duality, and which is also shown beautifully through double-slit experiment. However, these particles, they are, as Heisenberg wrote, they are both wave and particle, and neither wave nor particle. They are quantum objects with very specific properties. In 1900, Max Planck, while he was working on black body radiation, he discovered the energy quanta, formulated his famous energy frequency relation, E equals h nu, and that was the beginning of the quantum theory. It is interesting that Planck was also very interested in music. When he was young, he was even thinking between a career of a physicist and a career of a musician. So Planck played piano, cello, organ, composed operas and other musical works. In one of Peter Passage's books, there is a beautiful explanation of how Planck's musical activities might have influenced his physics. And so, in the second half of the 19th century, when Planck approached Professor von Jolly at Munich University, saying that he wants to study physics, Professor von Jolly said to Planck, "You should not study physics. Everything is already discovered. We already know everything about the world, so physics is done. There are only some tiny holes which needs to be filled." And Planck replied that, "I don't want to make any discovery, I just want to understand how the world works." And ironically, Planck was the one who made the who began this grand revolution and discovered the energy quanta, which overthrew all of the previous understanding of physics. Around the same time, Hendrik Anton Lorentz formulated Lorentz transformations, and Peter Zeeman discovered the very known Zeeman effect. And in 1905, at the age of 26, young Albert Einstein published 4 papers, including on Brownian motion, photoelectric effect, and of course his special relativity. And that year was called Annus Mirabilis, the year of miracles of Albert Einstein. If we come to the world of music, in 1899, Arnold Schoenberg composed Verklärte Nacht, which was one of the first compositions where Schoenberg went beyond the established tonal system. Claude Debussy composed La Mer, a symphonic work, and Ravel composed Gaspard de la Nuit for piano solo. Both of these works were exploring textural possibilities beyond the established paradigm. And Charles Ives composed the Unanswered Question, which is still one of the most mysterious works in American modernism, and one of the works which were symbols of the paradigm shift in music. In 1911, Rutherford discovered the atomic nucleus and published a paper about that. In 1913, Niels Bohr formulated his orbital model of a hydrogen atom. And even Albert Einstein was so astonished of Bohr's achievement that he said that this is the highest form of musicality in the sphere of thought. And later, Bohr's model was refined by Sommerfeld and later replaced by more updated and correct models. In 1915, Albert Einstein's general relativity was published. And in 1924, for the first time, the term quantum mechanics, Quantenmechanik, appeared in Max Born's paper, which was published in journal Zeitschrift für Physik. In 1924, Louis de Broglie, while working on his PhD dissertation at Sorbonne, he discovered the Patter wave. And in 1924, Satyendranath Bose, with the help of Einstein, published a paper which formulated Bose-Einstein statistics, which describe bosons, and its counterpart, Fermi-Dirac statistics for fermions, which was published in 1926 by Enrico Fermi and Paul Dirac. In music, during this period, the 5 last piano sonatas of Scriabin is a great example where instead of a traditional tonal system, we can observe a gradual shift to much more newer and more radical tonal approaches, as in tonal systems as well as in the texture. In 1913, Igor Stravinsky's The Rite of Spring was premiered in Paris, and by some scholars it was called the beginning of modernism in music, or the beginning of modern art. And in 1923, Schoenberg composed Suite for Piano Opus 25, which, according to Hershkovich and some other researchers, became the very first fully dodecaphonic piece composed for piano. And other discoveries and breakthroughs were made also in other areas. In 1915, Kazimir Malevich painted his famous Black Square, and Malevich was very well aware of developments in the world of physics. He even wrote about the importance of zero and the void, and he wanted how he can express them in painting. And James Joyce published Ulysses, which is one of the masterpieces of modernism. And the last chapter of Ulysses is where you have no single punctuation mark, which is a kind of indeterminacy in literature, in a style of the stream of consciousness. And finally, one of the reasons why 1925, this year, is celebrated as 100 years of quantum mechanics and is the International Year of Quantum, is because in 1925, at the age of 23, young physicist Werner Heisenberg published Matrix Mechanics. And matrix mechanics was the first mathematical formalism and mathematical formulation of quantum mechanics. In 1926, Erwin Schrödinger published his equation and formulated wave mechanics. In 1925, Pauli published his exclusion principle, first for electrons, and then it was extended to all other fermions. And in 1927, Heisenberg published his famous uncertainty principle. And in 1928, Dirac published his relativistic wave equation. If you come to the world of music, Edgar Varèse composed integrales and arcana, where instead of classical tonal and pitch rhythm structures, the sonoristic and timbral clusters were leading the structurization and crystallization of form in music. And in 1936, Anton Webern composed Variations Opus 27, which essentially paved the way for the entire mainstream of avant-garde music and kind of laid the beginning for integral serialism of Boulez and later achievements of music. These breakthroughs were happening in other areas as well, with publication of, if we take continental philosophy, Heidegger's Being and Time, in analytical philosophy, Wittgenstein's Tractatus Logico-Philosophicus, and also in the world of mathematical logic, with Löwenheim's column theorem, Gödel's incompleteness theorems, and also further developments of quantum theory, like in 1932, John von Neumann published Mathematische Grundlagen der Quantenmechanik, mathematical formalism of quantum mechanics, and later Dirac's bracket notation. And this is called this very famous photo from 1927 Solvay Congress in Physics in Belgium, and it is sometimes called the most intelligent photo in the history of humanity. So here we have Einstein, Lorentz, Planck, Curie, de Broglie, Born, Bohr, Heisenberg, Pauli, Schrödinger, Ehrenfest, Debye, and Dirac is here also. So many other great minds. It was that conference where, when Heisenberg presented his uncertainty principle and Bohr presented his complementarity, Einstein stood up and said, "The God doesn't play dice." On that, Niels Bohr replied that, "Albert Einstein, don't tell God what and how to do." So now we come to the world of music. We know from Heisenberg's uncertainty principle, delta P, delta x more or equal to Planck's constant divided by 2 pi, which essentially means that we cannot simultaneously measure momentum and position of a particle with equal precision. So if we know speed of a particle, we don't know its position, and vice versa. Karl-Heinz Stockhausen was one of the greatest composers of the 20th century who was very well aware of all these developments in physics. In discussions with Theodor Adorno, Stockhausen even said that his music exhibited uncertainty principle, and in interviews to Robin McEnany, Stockhausen expressed an idea that he had to do in music the same of what Heisenberg did in physics. So this is the score of Stockhausen's Klavierstück 11 for piano solo. Here, there are 19 fragments, and the performer has to choose in which order to play these fragments. So, we know from the classical scores, let's take any sonata of Beethoven or any work of Isaac Albéniz or Manuel de Falla. Of course, performer can change many aspects of music. That's why we have great interpretations and other interpretations. But there is one thing that no performer can change in classical scores, which is the structure of the work. There is always one single line, one arrow of direction, only one possible trajectory. So there is only one possible trajectory from point A to point B. And so, even if you don't know this piece of music, you can take, if you hear any sonata of Beethoven, let's say, you took its score, and you find where the performer is playing. Just looking at the score, you know what was before and what will come after that. So you perfectly know the position in the score. And also, knowing the tempo of a performer, you can easily know where he will be at the next point. So in classical scores, there is always only one possible trajectory from any point A to any point B. And this very well corresponds with classical mechanics. The great French mathematician Pierre-Simon de Laplace, he even formulated an idea called as Laplace's demon, is that if there will be an intellect that knows the position and movement of every particle in the universe, then this intellect will predict the future. There will be no secrets. That was a very deterministic, classical, mechanistic view of the universe. But from quantum mechanics, we know that it is not the case. In quantum mechanics, yes, you can have a particle move from point A to point B, but if you are not measuring, if you're not making an experiment, you are not observing the particle, you cannot know exactly by which trajectory it is moving. In the sense that in quantum mechanics, there is no such thing as predefined trajectory when there is no measurement. Only when you measure a particle, you kind of establish its specific path. But it will be valid only for this measurement. So according to Heisenberg's uncertainty principle, when you measure a position of a particle, you can know only its position and not the speed. And when you measure its speed, you can know only its speed, but not the position. And this is not something epistemological. It's not that our ways of knowing this, like our instruments to conduct experiments, don't allow us. It is more that the nature is in that way. So in quantum mechanics, when there is no measurement, there is no predefined trajectory. And this was an idea which Karl-Heinz Stockhausen expressed in the score. Like in any classical score, even when there is no performance, there is still a very well predefined form. But in this composition, when there is no performance, there is no such thing as form. It exists in a superposition of possible forms. And only when there is a performance as analog of measurement, a performer creates the form, creates the trajectory of this piece. And this is a very important moment because every performance will be different. So every performance will create a new reality of this piece in a similar manner as experiment creates reality in quantum mechanics. Here is another example of a score. It's Solo for Sliding Trombone by John Cage, which is excerpt from Cage's Concerto for Piano and Orchestra. This score is an example of a different approach. So this score, in a certain sense, has predefined form, but every single aspect of the score has to be decided by the performer. So these are two contrasting approaches to indeterminacy in music. Stockhausen, in a very detailed way, determines what happens inside every fragment. But the general or overall form of this piece is uncertain. And here, there exists a certain kind of form in this piece, but every single detail has to be decided by the performer. Which notes to play, intensity, dynamics, articulation, technique, duration, rhythms, everything has to be decided by the performer. And speaking about uncertainty, as we already said, if you have a score of a classical piece of music, knowing where the performer plays now, you perfectly know where he was before and where he will be after. But in Stockhausen's score, even if you know that the performer is playing, for example, here, this information alone doesn't tell you what he played before and what will come after. Now, these are some possible examples of how composers implemented uncertainty in music. Another interesting example is from quantum entanglement. In 1935, Einstein, Podolsky, Rosen published a paper, and later this idea was taken by Schrödinger in the 1960s, developed by John Stuart Bell, who formulated Bell's inequalities. And recently, Zeilinger, Closer, and Aspect in 2022 won the Nobel Prize for experimental work on Bell's inequalities. So that's about quantum entanglement, that particles can be connected. From the point of view of quantum information science, one of the most important features of entanglement is when you have entangled particles or entangled qubits, information which you have from the entangled qubits is more than information taken from single qubits just added to each other. So it's an example where a whole is bigger than the sum of its parts. And here we have the technique which is called multiphonics on wind instruments. That's for flute, that's for oboe. And here, for example, here we have the tones. These tones appear in brackets because they do not exist on oboe. If you ask an oboist to perform them, an oboist will not be able to perform them separately because these notes are very much lower than the range of oboe. But when you play this multiphonic, this chord, you start to hear these tones. So when these tones, they do not exist on oboe separately, but they start to appear when you play the chord as part of the overall chord. Similar things happen here, that when you play fast tremolo, other sonoristic techniques of multiphonics in flute, you hear a fluctuation of many more tones than those which form part of the initial multiphonics. As it was already stated, many great physicists were interested in music. Albert Einstein played violin. He even said that Mozart's music is so pure and beautiful that I see it as a reflection of the inner beauty of the universe. And we already said about Max Planck, and Werner Heisenberg was a high-level pianist. And this is a photo of Werner Heisenberg with his children. Johann Heisenberg on cello and Wolfgang Heisenberg playing violin. So in Heisenberg's family, he had 7 children. All of them played a certain musical instrument. It was almost a rule that you can choose any profession, but you must play music. The only question was which instrument they choose. So music was an inseparable part of life of Heisenberg. He even met his wife at a concert where Heisenberg played the part of the piano in Beethoven's trio. And in the 1960s, when Heisenberg turned 60 years old, the state of Bavaria gave him, as a birthday present, the possibility of playing Mozart's piano concerto with Radio Symphony Orchestra of München. In 1922, when traveling to Salzburg to perform with orchestra in Mozarteum, I made a stop in Munich specifically to visit Heisenberg's grave in Waldfriedhof in Munich. And then one interesting example of uncertainty happened. The first day, when I was going from airport to the city, I asked the taxi driver to stop at Waldfriedhof. I came there, I found the cemetery, but it was closed. So I found the position, but not the time. The next day, I came in the morning, the cemetery was open, so I found the time, but I couldn't find Heisenberg's grave. So I found the time, but not the position. Then I had to do a measurement, go to administration and ask where is his grave, and after the measurement, I finally found his grave. And later, after that, I made trips to Germany to meet with the children of Heisenberg. That's son of Heisenberg, Martin Heisenberg, and his wife Apollonia. Martin Heisenberg is a distinguished neuroscientist and biologist. He researches brain and neurosystem of Drosophila fruit fly and made certain conclusions about free will. And he shared a great deal of information about their musical life. So Martin himself plays flute. From 1940s until 1976, almost every year, almost every week, Heisenberg's family were making house concerts, where they would play music together with the friends and the family. That's an example of a program. So they also had the so-called guest book, where they would write exactly what concert on which day they performed which program. And that's an example of house concert, where they played 2 works of Mozart. And when you see Solisten, Werner Heisenberg on piano, Wolfgang Heisenberg on violin, and Peter Kunze on viola. And it was conducted by Fridolin Mann, who is the grandson of Thomas Mann. Here is another program with works ranging from Handel to Brahms. And when you see in the program Vater, Klavier, it means that Heisenberg himself is playing piano. Later, I was able to meet with Christine Mann, who is the daughter of Werner Heisenberg, in Urfeld am Walchensee. And that's one of Heisenberg's upright pianos. And she showed me the collection of Heisenberg's audio, the music which he liked to listen. And this is a collection of scores that Heisenberg played on the piano. So yes, Heisenberg was not only well aware of music, but he was very interested in composition and music theory. He took some lessons in counterpoint and music composition. And in the 1930s, he was even preparing a talk called Mathematical Structures in Beethoven's Piano Concerto No. 5 Emperor for his colleagues, professors in Leipzig University. And from the condition of the scores, you can see what kind of music Heisenberg played the most. In 1933, after getting the Nobel Prize, the first thing that Heisenberg bought for the money of the Nobel Prize was a grand piano, Blüthner grand piano, which still exists now in a very good condition and is being preserved in the house of his daughter, Barbara Blum. During my trip to Switzerland, I was able to meet Barbara Blum, and that's me playing on a piano of Heisenberg, the same one which he bought in 1930s for the money from the Nobel Prize. And that's with Barbara Blum. Even nowadays, we have numerous great scientists who are interested in music. This is Professor Brian Josephson. He's a Nobel Prize winner, very well known for Josephson effect. And this is a photo in Trinity College with first edition of Newton's Principia Mathematica with some handwritten notes of Newton. Professor Josephson is not only interested in music, but he also writes music. He composed a piece of music called Sweet and Sour Harmony, and currently we are working on a piano transcription of this piece. And Professor Josephson also published an article about music theory. The article is called "What Music Can Tell Us About the Nature of the Mind, a Platonic Model." That's me working with Professor Josephson on the piano transcription of his composition. That's distinguished biologist, Oxford professor Dennis Noble, who is also a musician, and he published a book called The Music of Life, where he explains systems biology through musical metaphors. This is famous mathematician Ian Stewart, who also plays guitar and is interested in mathematical aspects of music theory. This is David Politzer, the great physicist who got the Nobel Prize for discovery of the asymptotic freedom of quarks. David Politzer plays several musical instruments, especially banjo, and in Caltech he teaches a course called The Science of Music. And this is the great physicist Gerard de Hooft, who also plays piano. This is a photo made last year during my trip to Utrecht. In 2018, I was lucky to visit CERN as part of the government delegation of Kazakhstan. So here is me. And Fabiola Gianotti, who is the current Director General of CERN, in addition to her education as a physicist, she is also a graduate of Conservatorio Giuseppe Verdi in Milan, in Italy. So there are many great physicists who have a keen interest in music, who not only love music, but they actually interested in music theory and composition. During my visit to CERN, I was pleasantly surprised that many physicists know very well what happens in the world of music. One physicist actually told me that his words, "I do not like the music of Stockhausen. It beats my ears, but I have to admit that this is the music which changes the world." So these were the direct words of this physicist. And after hearing this, I thought that one important thing is that when many people operate with the words, "I like it" or "I don't like it." If you speak about cheesecake or some food, yes, this is probably appropriate. But when we are speaking about high art and music, it is much more appropriate to say, "I understand it" or "I don't understand it." After the visit to CERN, I composed a symphonic piece called The Sacred Universe of Particles, where I tried to musically show the movement of particles and some aspects from the standard model. So yes, CERN is a place where in 2012 they discovered a trace of a Higgs boson, also called as God particle, for which Higgs and François Englert were awarded the Nobel Prize. And yeah, Higgs boson describes how particles have mass. Here is a score of my composition Ombre del Vuoto. It is called in Italian because it was premiered during my postgraduate doctoral studies in Italy. So in Spanish it would be Ombras del Vacío. This is a musical implementation of the ideas of the shadows of the void. In music we have chords which include all the intervals, including their interrelations. So, for example, a tetrachord, which has all the intervals, including their inversions. Then I do the mirror image of this chord. I overlap them together. I get one chord of 6 tones. Then I make its mirror image. I get the second chord of 6 tones. I finally overlap both chords and get like a superchord of 9 tones. And this composition has 9 phases of development, and each phase is devoted to the spectrum of one tone from this chord. So this chord essentially decided the evolution of the entire composition. Everything's there. But this chord is not present in the composition itself. So this is an example of something which kind of doesn't exist, but affected everything which exists there. Another composition which is called Serenade of Invisible Stars. The idea came from the notion that when we look into the sky, we think that we see we think that we look into the future, But actually what we see is the past. Light travels 300,000 kilometers per second, and from Sun to Earth, it takes 8 minutes for light to come, and from one side of the galaxy to another, it can take millions and millions of years. And our galaxy is almost invisible. It's so small that it's literally not visible in the current observable universe. So when we look into the stars, the light travels millions of years to come here. And when we look at them, this star or this constellation may not even exist now. But we see it because it came only now. So actually, when we look into the sky, we are seeing the past. There are some other examples of music compositions of mine which were inspired by quantum theory. So for example, this is a symphonic picture called Time Run. And epigraph of this work is that people say time passes, time says people pass. Just a few days ago, in Oxford, in the UK, there was a world premiere of my new composition called Quantum Universe, Symphony for Organ, Quantum Guitar and Electronics. And this was the very first proper piece of quantum music, and the first time that organ, one of the oldest instruments in the world, was entangled together with quantum guitar, one of the newest instruments. And here are some examples from the score. And so finally, Werner Heisenberg wrote that many people think that science is objective while art is subjective. But this is not always the case. Science is not the nature itself. It is our view of nature. And it's which questions we ask about nature and how we try to find answers to our questions. And this depends on the overall level of civilization of development of human mind. In the same manner, a direction or a style or technique in music is not something really subjective. It is something formed according to the development of human mind. And so, as Heisenberg concluded, science and art are different languages in which humanity speaks about the universe. And just for, let's say, just for relaxing, I'm going to show you a very short piece of music. This is not quantum music. This is just a normal piece of music. It's my symphonic work called The Will to Live. I wrote it when I was 14 years old. And this is a video of performance during my first visit to Spain, which was performed in Alicante. Yes, so the idea of this piece was that the will to live is stronger than fear. This is the reason why it's called the will to live. Sí, finalmente, muchas gracias por atención. Si hay algunas preguntas, por favor. Pero es mejor de hablar con micrófono.
Okay, in English, Spanish, doesn't matter.
In English would be better.
Okay, thank you so much again. I have two questions. I've been thinking about when you were presenting the most intelligent photo, and you mentioned the uncertainty principle, and very briefly you said the complementarity too.
Yeah.
And then you presented like the two approaches of Stockhausen and John Cage, referring to the uncertainty principle. And I was wondering if there is any approach on the complementarity principle, so if there's any study musicologically on the matter wave duality. This is one question. And the other one that I have is more like a curiosity. And if you you said that contemporary, it's a concept, and it's a concept related to the present moment that we are living. So in some point, music was contemporary to its time. And I was wondering if you thought about like talking about all the musicians that you presented in this timeline, if we could put a different name, I don't know, different from contemporary. I don't know if you thought about that. That's how.
Okay, to your first question. Yeah, the first point is that uncertainty principle of Heisenberg and Bohr's idea of complementarity, they may look similar at first glance, but fundamentally they are very different. The complementarity and uncertainty are extremely different. They can have almost similar or close starting point, but they are looking in different directions. About complementarity, there was a great Italian philosopher, Umberto Eco, and he has a work called Opera Aperta. In Spanish it would be Obra Abierta, and it has been a very influential book. And in this book, Umberto Eco essentially discusses how different fields of art, including music, visual arts, and literature, were trying to implement complementarity, as well as uncertainty and some other quantum phenomena. So I think you can have more information if you look there, since it was one of the first examples when any scholar was digging into this question. About the second, the naming, it is always a curious question because, for example, I don't think that there was ever any era which named itself. Like, I don't think that like classics, what we call like ancient Greeks, they were not calling themselves ancient. Like antique and ancient Roman Empire, they were not calling themselves ancient. Baroque didn't call itself Baroque. Beethoven didn't call itself classicism and romanticism and so on. So all these names were given after, and actually after considerable time. It's now that we call ancient Greeks ancient, they're ancient for us. I mean, of course, being ancient is an interesting question because like Cleopatra, it's an interesting example that Cleopatra, she was not Egyptian, she was actually Greek, from Greek dynasty, and she was almost 3,000 years after the pyramids. So to her, pyramids were as ancient as she is for us. So what these people considered ancient was very different from what we considered ancient. And obviously Middle Ages, they didn't call itself as Middle Ages. It was name appeared after. So all these periodizations and the namings of eras were done after. And it is quite natural that we still call what we do contemporary. But if we want to know what our time will be called later, maybe in some hundreds of years, I'm also very curious. So I will be also very interested to see what the future generation will call our time. But that's something which we have to leave to the future generations.
Hi, all. No? Yeah. But you still think that, like Schoenberg, for instance, it's contemporary to us? Or we must wait like more time to be capable of sorry.
I mean, this really depends on the audience. Like for many of my colleagues, avant-garde composers, Schoenberg is extremely ancient composer. So for many of my colleagues, even Lachenmann, Fernichou, Griset, Dufour, those great names are already ancient old classics. So for us, contemporary music is what we do, like people in the generation of, let's say, from my generation up to, let's say, those who are under 40 or 50. But if you speak with the general audience, then yes, Schoenberg is called contemporary. So this is always a question of perception and what you call, but normally I would say that the convention is that given that Schoenberg and his time was when they made the revolution in tonal system, changing from old tonality to dodecaphony, that's, let's say, like a breaking point in when we, let's say, start counting avant-garde music.
Thank you. I have another one.
Well, I mean, it's good we can discuss it later. Maybe it's better to give some other people also the possibility to ask questions.
If there are any more questions, suggestions, comments.
you. What a fascinating conference. My question is quite different. You mentioned the conference, but part of the conference was about the beginning of the 20th century, where the physics explodes and made, suppose, a very important change. But there not only was a change in physics, but was a change in all the society. And in music, it influencing the operation of other kind of popular music. I mean, jazz, blues, all these things. Do you think that is somehow related?
Well, yes. I mean, it is true that it was a time of not only, as I said, not only revolution in physics, but in all other areas. So it was also the time when jazz, blues, and other areas of music were being developed, and early jazz even had some influence on classical music, especially on impressionists like Debussy and Ravel in their works. But so the thing is that I'm a specialist in classical music, so jazz and some other areas, they are quite outside of my area of expertise, so that's why I'm not making most of the comments on that. But specifically about jazz, there is a book by Stefan Alexander called The Jazz of Physics, where you can have more information.
Okay, thank you.
Thanks again. After your talk with us yesterday at IGFAE, I tried to check Stockhausen music, and I found this amazing piece that it was 3 orchestras with 3 directors, and they were playing at the same time. I don't remember the piece.
Gruppen für 3 Orchestern.
Yeah,
It was called Gruppen, yeah.
So I was watching it before with Mariano at CESGA, and we were wondering how this works. Can you give us some hint about how 3 orchestras with 3 directors?
I mean, that was a unique piece by Stockhausen, almost an experiment, which is one of the most extremely elaborate pieces of music regarding the structures. I would say that music theory and the work behind there is no less complex than some of the most advanced mathematical theories. Essentially, I think there should be a video with how Stockhausen worked with the 3 conductors, how to make them correlate with 3 different systems. I assume that there should be some videos about that. I think I have seen some. So, I mean, if I start explaining, it will take very long time, so it's better just to look there. At least Stockhausen Foundation and Stockhausen Archive, they definitely have plenty of information about that. Especially because Gruppen is one of the most well-analyzed pieces of contemporary music. And it's very good that you mentioned it, since it was one of the also most influential ones.
I will check that.
It seems we don't have any more questions. Oh, yes, we do.
I really liked your presentation, and I have a curiosity, what you have in mind to explore next? You have quantum, music, what about what next? Splitting of time or?
So, I mean, speaking of research, my next big project which I'm doing now is applications of mathematical logic to music. So like set theory, propositional calculus, predicate calculus, model logic, tense logic, and this kind of things to music theory. Normally it was before done working on pitches and frequencies and rhythms of music, but I am exploring how set theory and mathematical logic can be applied to timbral textural directions in music. So, for example, next year another book is going to be published, which is called Logic of Sound and Silence, Chaos and Order, which is one of the examples of what is about my research in the past few years. Currently, I'm also more interested about if there were any composers who tried to explore how the particle physics, like the standard model, and the physics of the 1960s and 70s, these discoveries very influenced music, but that's still ongoing research.
Thank you so much for this talk. I do believe we've ended all the curiosity here. Just take this chance to remind everyone, I'm going to switch. Mañana tenemos oportunidade de escoitar o piano. Recomendo que non perdades esta oportunidade. Temos plans para traelo para que nos dea un concerto que nos ofreceu, pero temos que contar para isto coa Fundación da Catedral que nos permita escoitalo ao órgano, a ver se somos quen de traelo para o ano que ven, pero mañán podemos velo aquí ás 8 ao piano. Gracias, Di.